Now we are going to talk about the Fischer carbines. So here carbene is attached to the metal Ln M double bond C R H. So this is the general formula for Fischer carbene and Schrock carbene. So here this Ln should be pi accepting ligand, and this R should be pi donor ligand. Then only we call it as a Fischer carbene. Otherwise we will not call it as a Fischer carbene. Okay, so in Fischer carbines the metal has to attach to the pi accepting ligand, and carbon has to attach to the pi donor ligand. So this is the condition for the Fischer carbene. So now there are important things. We have oxidation state and hybridization, and that is singlet state or triplet state, and then we have which reaction it will involve, electrophilic substitution reaction or nucleophilic substitution reactions. These are very important in examination point of view. So first we go for the oxidation state. So here oxidation state means we are talking about the metal. So it's very simple, metal attached to the pi accepting ligand. So when metal will attach to pi accepting ligand, if metal is electron rich, so that will attach to the pi accepting ligand. If metal is electron poor, that will not attach to the pi accepting ligand. So here metal attached to a pi accepting ligand, right? That means it should be electron rich. If it should be electron rich means the oxidation state will be less. So oxidation state of Fischer carbene will be low. Okay, you are understanding, right? If we have M plus 1 and M plus 4, so this is electron rich and this is electron deficient. So this is having more chances to bind to the pi accepting ligand compared to M plus 4. So similarly, since here metal attached to the pi accepting ligand, the oxidation state of this metal should be low. In Fischer carbene, oxidation state of metal will be low. And before going to the hybridization, we just see whether it is singlet state or triplet state. Okay, now metal attached to the pi accepting ligand, that means there is some electron density transfer from the metal to pi accepting ligand. So automatically the metal will become deficient. So now there is electron transfer from the carbene to metal, that we will see in MOT diagram later. So the electron density will transfer from the carbon to metal. So now whatever electron density this carbon is having, that is giving to the metal. That means this carbon is become electron deficient, right? So we have a singlet carbene and triplet carbene. Among these two, singlet carbene is electron deficient in nature and triplet carbene is electron rich in nature. Okay, so since this carbon is electron deficient in nature, so the Fischer carbene is singlet carbene, not triplet carbene. Schrock carbene comes under the triplet carbene. Okay, so now we have a singlet carbene. We know that it undergoes sp2 hybridization, and the triplet carbon undergoes sp hybridization. So this Fischer carbene undergoes sp2 hybridization, and now we'll go for the electrophilic substitution, nucleophilic substitution. It's very simple that some electron density is transferring from this carbon to metal. This is electron deficient in nature, so it acts as an electrophile. That means the nucleophilic substitution reactions will take place. Fischer carbenes act as an electrophile, that means nucleophile goes and attacks to this carbon. So it's all points are very clear here. The first thing is pi accepting ligand should be present on the metal and pi donor ligand should be present on the carbene. And we have oxidation state, that should be low oxidation state, and hybridization. Before going for hybridization, we just need to identify whether this carbon is singlet carbene or triplet carbene. And if we see the MOT diagram, that we will discuss later, and the electron density from this carbon will transfer from here to this metal. So now this carbon is become electron deficient. If electron deficient carbon is there, that comes under singlet state. So singlet carbene, So singlet carbene undergoes sp2 hybridization. So Fischer carbene undergoes sp2 hybridization, and we can see a nucleophilic or electrophilic substitution reaction. Since this is electron deficient in nature, it undergoes nucleophilic substitution reactions. And this is the MOT diagram for Fischer carbene. So here we can see this is the pz orbital of carbon, and the electron density is transferring from the pz orbital of carbon to carbon to an empty orbital of metal. Okay, so because of this region, this is the electrophilic in nature. Okay, so now we have a bond order. So we have M double bond C, M single bond C. So the bond order of this is 2. Bond order here is 1. So bond order is inversely proportional to bond length. This we know that. Okay. So compared to these two, this should be having a more bond length compared to M double bond C. And where in case of Fischer carbene, the bond length will lies between M double bond C and M single bond C. This is the bond length of Fischer carbene. So this is expected to be equal to M double bond C, but compared to M double bond C, the Fischer carbene M double bond C bond length is more. That means here bond order is exactly 2, but in this case bond order lies from 2 to 1.5. So this is the reason why in Fischer carbene M double bond C bond length is greater than M double bond C. Okay, and when we compare Fischer carbene M double bond C and M single bond C, so here bond length will be lesser compared to M single bond C, because here bond order is 1, but bond order in this case is lies between 2 to 1.5. Why this bond order is decreasing? Because here we can see that some electron density is transferring from the carbon to metal. That means it's supposed to be a double bond here. So some electron is giving from the carbon to metal. That means the bond are also decreasing. So this is the reason why in case of Fischer carbene M double bond C having a more bond length compared to M double bond C, free M double bond C I mean. And in case of diborane, we take diborane. Here we have 3-centered. This is the structure of diborane. So here we have 3-centered 2 electronic bond, right? So in case of Fischer carbene, we have a 3-centered 4 electronic bond. In case of Fischer carbene, we have 3-centered 4 electronic bond. We can see in this MOT diagram. So there are 1, 2, 3, 4 electrons. So is having 3 center. One is metal center, another one is carbon center, another one is this pi donor ligand. So 4 electrons are lies on the 3 center. So because of that reason, in case of Fischer carbene, we have a 3-centered 4 electronic bond. In case of diborane, we have 3-centered 2 electronic bond. This is very, very important. And now we'll go for the synthesis of the Fischer carbenes. So first one is we have vanadium CO6 plus pH Li. So now for our convenience, we will write this like this: C triple bond O and here CO5. So we know that pH is nucleophilic in nature, this is positive in nature. So this carbon is electrophilic in nature. So this pH comes and attacks to the carbon. So then it will become double bond C pH and this bond goes like this, and this will become O minus and Li plus. Okay, now we have a methylating agents. We can take CH2N2 as a methylating agent, or we can take there are other methylating agents also. So if we will take those methylating agents, just this O minus will get converted into OMe, PH OMe. So this is the for the Fischer carbene. This is the way to synthesize Fischer carbene. And we can take a methylating agent as a Me3O plus, BF4 minus also we can take, or FSO3 CH3 also we can take. If we will take FSO3 CH3, this will exist like this, FSO3 minus and CH3 plus. So this CH3 plus goes and attacks here. Okay, then it will become OMe. Okay, so and the next preparation method is, so here we have iron, and PPH3 CO double bond O R. Here we have FSO3 CH3. So this is also methylating agent. So here this will dissociate into FSO3 minus and CH3 plus. And here the polarization will be towards this side. Here negative charge comes, here positive charge comes, and this F minus comes and attacks here. And there is a development of a double bond here, so that finally will end up with Fischer carbene, PPH3 CO OMe R. So these are the two methods to synthesize the Fischer carbene. So as we know that the Fischer carbene is a electrophile in nature. That means the nucleophilic substitution reactions will be favorable at this carbon center. So now we will see some of the nucleophilic reactions on this carbon center. First one is, we have CO5 Cr double bond OMe Me plus NHR2. So as we know that this carbon is electrophilic in nature, this lone pairs goes and attacks to this carbon, and it becomes CO5 Cr OMe NHR2 and methyl. So now we will remove this one as a methanol, then we will get CO5 Cr. Here double bond will regenerate again, NR2 methyl. So here we can say nucleophile is going and attacking to this electrophilic carbon. And then we have a cyclopropanation also, that looks like this, CO5 Cr OMe pH. We'll just heat it in the presence of some temperature, so that leads to removal of one carbonyl group. It will become CO4 Cr double bond OMe and pH. So now we'll treat this one with the one dienophile, so that here 2+2 cycloaddition will take place. It will become CO, CO4 OMe, pH, and X and Y. So now we'll just remove this, and this bond goes like this, and this bond comes here. So there is a generation of a cyclopropane ring we'll get. pH XY plus CrCO4. So here also we can see the nucleophilic center is going and attacking to this electrophilic carbon. And then we have Diels-Alder reaction also. In this Fischer carbon we can say Diels-Alder reaction also. We have diene here, and here we have Fischer carbon. So here we will get endo product. Always in the Diels-Alder reaction we will get endo product as a major product. So here we will end up with CrCO5 and OMe. So this is about the Diels-Alder reaction in the Fischer carbenes. And then we have aldol reaction also here. Aldol reaction. We'll take same example, CO5Cr double bond OMe with ethyl group, and we will take a base here. So this will be this will be highly acidic in nature, so this proton will be abstracted by the base. After abstracting, it will become a negative charge is here. So now aldehyde comes into picture. So this electrophilic carbon goes and attacks to this negative charge, so that we get OMe, OH, pH. So this is the aldol type reaction. And last reaction is we have a Michel addition reaction. Here we have Michel addition reaction. Have CO5 Cr double bond OMe plus O minus La plus. So this bond comes like this, and this will become negative charge, and here this is the nucleophilic center, and directly this nucleophilic center goes and attacks to, and this polarization will be like this. This goes here, this comes here. So now this is a positive charge here, and this negative charge coming and attacking to this carbon, so that it will become CO5 Cr, negative charge here, OMe double bond R. So here this negative charge comes like this, so that here there is a development of the double bond, and this double bond goes here. So here negative charge comes, and here also polarization will be like towards this side, and on chromium we will get a negative charge. So since it is electrophilic in nature, so this nucleophile goes and attacks to this carbon. So this is about the Fischer carbene. Thank you.